so in the first video we talked about special vectors for a specific matrix. So now we want to define that for all matrices. We want to find these special directions where the action of the matrix is super simple. Alright, so I'm going to start with an n by n matrix, A. And let's assume I have one of these special vectors. So let V be a non-zero vector in Rn. Right, so if you remember from the last example, the blue vector stayed the same, the red vector flipped. So really what we have is we have these two directions that are preserved by the vector. Maybe not each vector is preserved, but the line is. So every vector on it is sent somewhere else on the line. So that's what we'll ask here. So V is an eigenvector of A if it's sent to a multiple of itself by A. So if there is a lambda, right? Lambda is the Greek letter for L. In R, so that AV is lambda V. Alright, so A times V is just a multiple of V, it's on the same line. As soon as we have that, we'll call it an eigenvector, and then lambda is going to be special as well. That real number is going to hold information. We'll call that an eigenvalue. So lambda is then an eigenvalue for the matrix A. Alright, so in the example we had over there, the two vectors, the blue and the red, are both eigenvectors with different eigenvalues. So this one was, that one was 1, 4, is an eigenvector for A with the eigenvalue, well that one was preserved, so the eigenvalue is 1. And then the red one is an eigenvector with eigenvalue minus 1 because it's flipped by A. So that one was minus 4. 1 is an eigenvector for A with eigenvalue this time lambda equals minus 1. So this is we've done all the work before. Let me just remind you what that matrix was, especially if you didn't see that video or it's been a while. So A was minus 15 over 17, 8 over 17, 8 over 17, and 15 over 17. Alright, so those special values that helped us figure out what the matrix was actually doing, those are called eigenvectors, and the eigenvalue tell us what the action is on those special values. All right, that's great. How do we find these eigenvalues? How do we do it algebraically so we can understand the geometry? So I need a theorem. Here's the theorem we want. Again, we're talking about square matrices. That's the only place where this makes sense. So A will be an n by n matrix. What I want to find the eigenvalues first, then lambda is an eigenvalue for A, if and only if, so it's equivalent to the determinant of A minus xin being the same as 0. All right, so this is going to be a determinant, but the matrix depends on x. So this is going to turn out to be a polynomial in x. So when we want to find the eigenvalues, we'll just look at computing this determinant. We get a polynomial, we find its zeros, we have the eigenvalues, and then hopefully we can find the eigenvectors from them. All right, so let's prove this. All right, so let's assume that we have AV equals lambda V. That means V is an eigenvector, lambda is an eigenvalue. I'm going to send this to the other side. Oh, sorry. I meant... Oh, here's the answer. Here, we're using lambda here, so it should be lambda here as well. When we'll do examples, we'll use x, but for now, because there's a lambda in this, there has to be a lambda in this. All right, so this is the same thing. I'm going to send lambda v to the other side. So that will be the 0 vector. Careful, these are vectors. I'm going to factor v. Now I'm going to give you a second to look at this and tell me what's wrong with it. This makes no sense. It's a matrix minus a value, so to make sure it makes sense, I'm going to put an identity matrix. So A minus lambda inv equals 0. That means that V is in the null space of A minus lambda in. All right, so if you have an eigenvector v for value lambda, that means there's something in the null space. So, see? So if lambda is an eigenvalue, that means that you have a v like this that's not 0. That has this property, so it has this. V is in the null space of A minus lambda I n. And that's only true that a null space is not just a zero space. That's only true if the matrix is non-invertible. So, determinant of A minus lambda I n is 0. There you go, that's what we need. We have something that we can solve for, we have a polynomial, we'll be able to find the zeros, and that's awesome.